When you use a ZK rollup, your transaction follows a short pipeline before it is final on Ethereum. Submitted, ordered, batched, proven, settled, and finalized. That pipeline is what gives rollups lower cost execution while still inheriting Ethereum security. So far, you've built the foundation. Why Ethereum needs scaling, how Layer 2s reduce cost and congestion, and what zero-knowledge proofs add to rollups. Now we'll turn that architecture into a timeline, following one transaction as users, sequencers, provers, contracts, and Ethereum each play their part. A ZK-Rollup transaction enters the rollup first, rather than going directly to Ethereum. The rollup orders many user actions, executes them off-chain, and groups the results into a batch. A prover then creates a validity proof showing that the batch was computed correctly. Ethereum verifies that proof and accepts the resulting state update. That is the core trade-off: off-chain execution with on-chain verification. The lifecycle begins when a user chooses an action, such as sending tokens, swapping, minting, or calling a contract. The dApp passes that request to the wallet, which builds the transaction with details like recipient, value, call data, nonce, and estimated fee. After the user approves it, the wallet signs with the private key, proving authorization without exposing the key itself. The signed transaction is then sent to a Layer 2 rollup endpoint, even if the experience feels much like using Ethereum directly. After submission, the transaction still does not go straight into a block. Rollup infrastructure first receives it, often through an RPC endpoint or transaction gateway. From there, it waits in a pending queue with other transactions. The sequencer decides what to include and in what order. This queuing step matters because it affects confirmation speed, fee competition, and how much users must trust the system for fair inclusion. The sequencer acts as the rollup's traffic controller. It collects incoming transactions, orders them, and prepares them for execution, so the rollup can produce its next state update. Because this happens quickly, users often receive a soft confirmation that their transaction was accepted. But that signal is still provisional. Stronger assurance comes later, once the relevant data and proof are settled on Ethereum. Once transactions are ordered, the rollup executes them off-chain, outside Ethereum's normal execution environment. Balances move, contract data changes, and account nonces advance. After every transaction is applied according to the rollup's rules, the overall state has changed. The rollup summarizes that new state as a state root, a cryptographic fingerprint that Ethereum can later verify with a proof. Rather than paying Ethereum for every user action individually, a ZK rollup groups many actions into a single batch. The fixed Layer 1 cost is shared across everyone in that batch, which lowers the cost per transaction. Larger batches can improve efficiency, but they also create trade-offs. Users may wait longer, and the proof may take more time to generate. Rollups tune batch size based on demand, fees, and design goals. Batching reduces how often a rollup talks to Ethereum. Compression reduces how much it says each time. The rollup can remove repeated fields, use compact encoding, and post only the data needed to reconstruct or verify state. That smaller footprint matters because Ethereum block space is scarce and priced by demand. Still, compression cannot discard security-critical data. Lower fees only work if the system still has enough data to be checked. After the batch is executed, the rollup must prove that the old state correctly became the new state under the rollup's rules. This proving work happens off-chain and can be expensive, often relying on optimized software or specialized hardware. The result, however, is compact: a validity proof. Ethereum only needs to verify that proof, giving strong assurance of correctness with far less on-chain computation. Proof generation is expensive because the prover must translate real transaction execution into constraints and circuits, then prove that every step was followed correctly. More complex smart contract logic increases the proving workload. Teams reduce this burden with parallel processing, specialized hardware, and recursive proofs, but those choices add engineering and infrastructure cost. Verification on Ethereum stays lightweight because the heavy work has already been done off-chain. At this point, the rollup gives Ethereum the evidence it needs: the batch data, the proposed new state root, and the validity proof. Ethereum's rollup contract receives the package, and the verifier contract checks the proof. The key idea is efficiency. Ethereum does not replay the full Layer 2 workload. It confirms that the submitted proof is valid. Once accepted, the new state root becomes the recognized, settled state of the rollup. Settlement is the moment the rollups update is accepted by Ethereum under the rules of its rollup contract. For a ZK rollup, that means the submitted proof and state transition have been verified on-chain. Once accepted, the new state root is anchored to Ethereum consensus. This is why users can treat Ethereum as the final source of truth for the rollup. Finality is different from fast confirmation. A user may see a transaction accepted by the rollup almost immediately, which creates a smooth experience. The stronger security guarantee arrives later, after the batch is posted. The proof or state update is accepted on Ethereum, and the data is available. Withdrawals depend on that finalized state. The bridge should release assets only when Ethereum can enforce the rollup's result, not merely after a rollup level signal. A ZK-Rollup is more than fast off-chain execution. Transactions are submitted, ordered, executed, compressed into batches, proven, and settled on Ethereum before finality. The core question is always, what can Ethereum verify, and is the needed data available? That leads directly into the security assumptions and trade-offs behind rollup design.